Well, guys, have become experts at the calculation of pH of strong acids and strong bases, at the calculation of pH of weak acids and weak bases. You've also become quite acquainted with the calculation of acidic salts, which are just like weak acids, or basic salts, which are just like weak bases. We still have to do some calculations with the amphoteric salts, but that will come a little bit later on. For now, you are now right at the stage where you'd be excellent in calculating the pH of polyprotic acids and polyprotic bases, which is why we're going to discuss this at this moment. First of all, what are polyprotic acids? Well, they are substances that can donate more than one proton, H3O plus I mean, in solution. Well, until now, we only took acids which can, give up a single proton to water, giving you H3O plus. Now we're going to look at acids such as H3A, for example, which has 3 acidic proton in itself, such that it can give up the first proton to water and donate it to water, becoming H3O plus, the water becoming that, and H3A becomes H2A because it lost a proton and with a negative charge. This is governed by, this is actually a reversible reaction. It's not a complete reaction. And most polyprotics are of this sort. We're going to look at one exception, and that will be in the problem set. That's for the H2SO4. This amount of H3O plus is governed by the Ka, and we call it Ka1. The reason is because we have another acidity that is possible. Now the H2A minus can come in, also donate a proton to water, becomes H3O plus, and this becomes HA2 minus because it lost a proton, gained another extra negative charge. This equation is governed by a Ka as well, but we call it Ka2. And Ka1 and Ka2 are never the same, okay? So the amount of H3O plus coming from the first equation will never be the same amount as that from the second equation. And in this case, even the HA2 minus also has a proton which can be donated, and thus it also can donate its proton, and HA2 minus becomes A3 minus, lost a proton. And a third H3O plus is produced. Again, the Ka3 in this case is never the same as the above. And usually Ka1 is much bigger than Ka2, and that is way much bigger than Ka3 in the majority of cases, actually in all cases pretty much. What are polyprotic bases? Well, polyprotic bases are substances that can accept more than one H plus protons in a solution, or in other words, release more than one OH minus. What do you mean by accept an H plus? From where does it accept it? Well, it accepts it from water. Now, water is going to act as my acid because I have a base. So I have a base such as A3 minus now in solution. Notice there's a negative charge, so it's a fairly decent base. It's a strong enough base. Well, not a strong base. Again, all of these are weak bases, but it's a negative charge. It's not just neutral. And from organic, you know that that's a stronger base if it's negative than neutral. Thus, this can accept a proton from water. Water becomes OH minus now, and A3 minus has become accepted a proton. It has become HA2 minus, lost a negative charge, gained a positive charge. This is also a reversible reaction, and it's governed by a Kb value. Well, we call it Kb1 because, again, look at this reagent Ha2 minus, there is still 2 negative charges. And yes, those 2 negative charges can also accept another proton, thus becoming H2A minus and OH minus. There also has now become OH minus, and we've released another hydroxide ion into solution. The amount of hydroxide ion in this equation is never the same as the above, and usually the first basicity is bigger than the second. Wait a minute, H2A minus can also, wait, it has a negative charge, it can also possibly accept a proton from water. And it's finally become neutral, it's become H3A, but it has released another OH minus. And thus, in this case, we call this a triprotic base because it can accept up to 3 protons or release up to 3 hydroxide ions. This is a triacid. It can donate up to 3 protons and release thus up to 3 OH minus, OH plus ions into solution. Well, we took the extreme case. We went all the way to the triprotics. Of course, there's diprotics, which are simply like H2A. Now, this is just on a side because I won't have another place to put it, but I thought it was okay to put it here. We're going to use this actually when we get to titrations. 1 mole of H3A has 3 protons, right? And it can donate up to 3 protons. And so if I was actually using a titration, a complete reaction to completely neutralize this acid, I will need 3 moles of OH minus to neutralize it completely. Likewise, in the case of base, for 1 mole of A3 minus, this actually ends up producing 3 moles of OH minus if the reactions go to completion. And thus, to neutralize all the negative charge here, I will need 3 moles of H3O plus for complete neutralization of this tribase. We will see this later on. Don't worry too much about it at the moment, but it's just a place for me to put it. Now we're going to look at the relationship between Ka and Kb, but using a particular example, which is my favorite H3PO4, which is a triacid. Now, I'm really not going to get into these equations. Read them on each part of the equation. Just here I have H3O plus, it becomes H3PO4, it becomes H2PO4 minus. Why? Because it lost a proton to water, acting as an acid. This first acidity is governed by a Ka1, and of course, if I want to write an expression for Ka1, we do products divided by reactants. So that's going to be H2PO4 minus times H3O plus divided by H3PO4. Concentration at equilibrium. And so don't forget, these concentrations are at equilibrium for each of the Ka expressions. Now I just want to point out, I want you to look at the Kas and look at the 2 species. So I can say Ka1, but I could also say this is the Ka for H3PO4 slash H2PO4 minus, which is the acid-base couple in this equation. Again, now the H2PO4 minus can also donate a proton to the water, and it's now ends up losing this proton and it becomes HPO4 minus, producing H3O plus. Now we get Ka2, also products divided by reactants, and this moves on. The HPO4 minus loses another proton, gives it up to water, and it becomes PO4 minus because it lost that proton. And again, Ka3 in this case, because this is an acidic reaction, is products divided. PO4 minus divided by HPO4 minus. And so usually Ka of the first couple, which is an H3A, H2A couple, is greater than the Ka of the second couple, which is at H2A, HA2 minus, H2A minus becoming HA2 minus, and then the HA2 minus becomes H3 minus. So this is H2A minus couple becoming HA2 minus, and the last couple is an HA2 minus becoming an A3 minus. Of course, the first acidity is greater than the second, greater than the third, and thus the pKa1 will be less than pKa2, which is going to actually be way less than pKa3. Let's look at the base now. For the same couple, actually, type, so if I actually now start off in solution with PO4 3 minus, of course, what will PO4 3 minus do in water? It's not going to act as an acid, absolutely not. It has no protons. What will it do? It will react as a base, picking up a proton from water, and the water becomes OH minus, and it becomes HPO4 2 minus. Now, what is the governing equation here? It's a Kb because it's a basic reaction. Okay, it's a basic reaction. So what do I have? Products divided by reactions, OH minus, HPO4 2 minus divided by PO4 3 minus. What can happen then? Of course, now this can continue. Look at the HPO4 2 minus. It still has negative charges, and voila, yes, it can react with water in another basic type reaction. Picking up another proton from water, water releasing OH minus into solution, and I still have now this new species, H2PO4 minus. The equation is governed by a Kb2 because this is now the second basicity that's occurring, and the Kb2 is products divided by reactants for that equation, and as you can see, there it is. And we have a third equation. Of course, the H2PO4 also has a negative charge further, and yes, it possibly can pick up another proton. HO minus is released again, and H3PO4, and it stops actually here because there's no more negative charges which it can pick up a proton with. Okay, and no more electrons actually to pick up another proton. So it actually stops at Kb3 in the basic form. And of course, you can write an expression, products divided by reactants as usual. Now, of course, in this case, as in the above for acids, Kb1, the first basicity is more basic than the second basicity than the third basicity. Okay? Now, as you all now already got a gist of, we usually don't give you Kb values, guys. We always give you Ka values for any two couple, and it's up to you to get the Kb values. So how am I supposed to get the Kb value? Say Kb1. How do I get Kb1? Well, I usually get it from a Ka, right? And you know that Ka times Kb is Kw. But if I want Kb1, and that's in green, which Ka should I choose? Okay. I actually have to choose Ka3. Tell me why. Because this Kb is for the couple HPO4 2 minus, PO4 3 minus. Who has the same couple in the Ka? Yes, absolutely. The Ka3 has the same couple. Ka3 is the Ka of HPO4 2 minus, PO4 3 minus. So Kb1, to calculate it, you need the Ka3 value. And actually Kb1 times Ka3, try it, multiply the two together, you notice that the species cancel out and you're only left with H3O plus times OH minus, which is Kw. And so you really have to watch out to which Ka value you have to choose when you need a Kb value. In the case of here, Kb2, if I need a Ka here, what Ka should I choose? I choose the Ka that has the same couple, H2PO4 minus with HPO4 minus. Who has that same couple in the acidity? Absolutely. It's also Ka2 in that case, H2PO4 with HPO4. Only, one on top of the other. So in the case of Ka2, they happen to be the same. Kb3, which Ka value do I choose? Again, look at the couple, H3PO4 with H2PO4. Yep, that's Ka1, all right. H3PO4 with H2PO4 minus. Okay, if you're given pKa values and you want a pKb value, it's the same thing. Take the minus log of both sides, you end up getting. Let's say, look at pKb1. pKb1 will be actually 14 minus pKa3. Why? Because from that first equation there, take the minus log of both sides, you will end up getting that. So that just helps me out sometimes if I want pKb values and if I'm given pKa values. And you could do the same for the rest. All right. Just a briefing here. Let's look at this species for a moment. Concentrate on the HPO4 2 minus. Okay, wait a minute. Here, on the bottom here, it's acting as a base. But up here, it's actually, what is it? Is it an acid or is it a base? It's actually amphoteric. At one point, because it has a negative charge, it can act as a base, pick up a proton from water, but it also has an acidic hydrogen, which can donate to water, and it's acting as an acid. So this is an amphoteric substance. H2PO4 is also another amphoteric substance. It also has a negative charge, so it can act as a base. But wait a minute, it has 2 protons, which can be donated, and it can act. Here's the exact pKa values of H3PO4 with the couple. There's a mistake here. Okay, so let's take a look here. Here's the pKa values. pKa values appear in increasing order, the full protonated H3PO4 being the strongest acid. So of course, H3PO4 is the strongest out of all of the 3 other acids. We already talked about the intermediates, which come about H2PO4 minus and HPO42 minus, and we said that they both have donor or acceptor properties of H+, and so these are amphoteric substances. If we look at the Ka1, Ka1 here would be 10 to the minus 2.1, right? Ka2 would be 10 to the minus 7.2. And Ka1, as long as it's 100 times greater than Ka2, which is usually much greater than Ka3, but if Ka1 is greater than 100 times Ka2, we are allowed to determine the pH from the first acidic couple alone and neglect all the other equations, the acidic equations, that is. What am I talking about? Well, you're not really going to understand till I solve an actual problem. Okay, so here we are, we're going to calculate. This is actually number 21 of your homework, part 4, and only the first part of it. Okay, so of H3PO4, which is 10 to the minus 1 molar concentration. And they gave us all the pKa values, pKa1, pKa2, and pKa3. And this is the order in which you have to do things. Do you really have to put the equations H3PO4 plus water becomes H2PO4 plus H3O plus, and then the rest of them? No. That should be always in your brain that this is a triprotic, so it can, do 3 equations. The first step you should ask yourself is, see if Ka1 is greater than 100 Ka2. If that's the case, look what can happen. Let's see, is Ka1 greater than 100 Ka2? Well, that's easy. Ka1 is 10 to the 2.1, 10 to the minus 2.1. Ka2 is 10 to the minus 7.2. And therefore, yes, you divide them by each other, you know, you can actually get an exact number, but you really don't have to. It can be mental. And you could always see, multiply the Ka2 by 100, you could see that that's much greater. The Ka1 is much bigger than that. Okay? If that is the case, we are allowed to neglect the second and third acidity, and we are allowed to consider only the first equation, and we treat it as a weak monoprotic acid. Okay? And so I only have a single equation, and I'm allowed to only use this single equation, which is like I'm treating it as a mono acid. Okay, and I forget all the other equations, and as if I only have a single H3O plus being produced. And now, guys, from here on, this is like a normal monoprotic acid. And of course, we already went through the calculation of pH of monoacids, and we had 3 different categories and 3 different validities, which we would use a particular equation depending on the concentration and the Ka value. So what's my next step, really? Okay. The next step, okay, I decided this is a weak acid, and is to see if the concentration, initial concentration in my solution is greater than 100 Ka, but not any Ka. This is the Ka1, okay, for this acid. Okay, so because we are given 3 Ka values, so which Ka value do I use? I only use the Ka1 because all the rest we said is insignificant. Well, you're all experts at this now. Take the concentration initial divided by Ka1 and see if that is greater than 100. Is it? Well, it's not. Look, 0.1 times divided by 10 to the minus 2.1. Again, I like this because the calculator does it for me. I don't have to think. I get a number, and I ask myself, is this number greater than 100? It's not. It's actually less than 100. So this is not valid. So C0 is not greater than 100 Ka. What do I do then? I have to see what equation am I allowed to use. What equation, guys? Come on. What equation do I have to use? C0 is not greater than 100 Ka. Just go ahead, use the quadratic at this point, okay? If C0 is not greater than 100 Ka, just go ahead, use the quadratic. There it is. That's the quadratic equation. Oopsie, I forgot. Where did that come from? Well, I memorized it. What if I forget? Well, it comes from the Ka expression. And what is the Ka expression? It's from this equation. And yeah, you could write down the equation and you could say this is H3O plus times H2PO4 minus divided by H3O plus, or simply X squared divided by C0 minus X, expand everything, and you get this equation. And like I said, if you really want to be fast, just memorize the quadratic. Easy. X squared plus Ka1 times X minus Ka1 times C, which is the initial concentration of whatever you have in the solution of the acid. Substitute everything in, guys. Okay, so you have to substitute Ka1, you substitute Ka1 times C, get a quadratic, solve for X. What is X? Yes, it's an acid. It is the H3O plus, okay? And so that's immediately pH equals minus log of the X, and we get 1.61. Very simple. All of this part you already know. This is just weak acid pH calculation. Now, if this was valid, of course, what would you use? Of course, you would use pH equals half pKa1 minus half pKa, half log C, minus half log C. All right, so the only difference is I have to do this first step. Okay, is Ka1 greater than 100 Ka2? And in this case, it's much greater than 100 Ka2. Okay, just so you know, on the majority of cases of weak acids, that is the case. If it's not, what will happen? Then I have a special case. It's a totally different thing. And that's going to be more like the combination of two weak acids. And we're going to look at mixtures of two weak acids and what we do when we get mixtures of two weak later on. Okay, so we actually started off with the hardest part, which is the triacids. And now I'm going to go back to the diacids, H2A. Okay. Well, guess what? It's the same process, guys. It's one less step actually to write down or not write down. And the best way to actually get into this is just by a direct example. Let's look at the pH of a concentration and the concentration of all species in a 0.5 molar carbonic acid. Well, if you're lucky enough, you'd know what carbonic acid is. And in our course, we will give you what carbonic acid is, okay? It's H2CO3. So frankly, you should know it. H2CO3. What is this? It is a diacid. Look, it has two protons which can be donated. Okay. There's the first acidity, donate to water, it becomes HCO3 minus, H3O plus, and then the HCO3 minus also has an acidic proton. It's going to donate it to water, it becomes CO3 2 minus. Whoops, no more donations. It has no more H pluses, so we stop at here. Okay, so Ka1, Ka2, so it's telling you it's a diacid pretty much. When I give you Ka1 and Ka2, I'm telling you it's a di. Watch out, I can give you Ka1, Ka2, and it's a really di base. But in this case, it's a diacid. So what's the steps, guys? First step, is Ka1 greater than 100 Ka2? Is Ka1 greater than 100 Ka2? We'll check it out. Ka1 is 10 to the minus 7, Ka2, 10 to the minus 11. Multiply this guy by 2, by 10 to the 2. Well, yes, that is still way greater. Okay, so I don't really need a calculation, but if you really want to, you could. So most of the H3O plus is actually going to come from the first equation. What am I allowed to do? Pretend that the second one doesn't calculation of the pH. And so the pH of this diacid is treated as if it's a weak monoprotic acid. What's my second step? Oops, too early. What's my second step? I'm doing a weak acid, guys, calculation. In a weak acid now, what do? I have to see, is C0 greater than 100 Ka? Which Ka? In this case, it's Ka1 because that's the equation that I'm looking at. Is it? C0 is 0.5. Look at the Ka, it's something 10 to the minus 7, so that's very small. And so yes, 0 is greater than 100 Ka1. You want to take the 0.5, divide by this number, see if it's greater than 100, be my guest. That is valid. Third step, what equation should I use? Of course, the equation which I have validated my approximation where x is negligible, and that's simply pH equals half pKa minus half log C, which pKa? pKa1. That's the only difference between weak acids and diacids. I just have to change this part. Instead of pKa, I put pKa1. You have Ka1, get the pKa value, and you are then done. Just substitute the C, the concentration, there's no dilution, so you use it as is, and voila, that's all you need. There's a little bit of a gypsy to this, is they want the concentration of all species in the solution. What species do I have? Well, of course I have whatever species are coming from the first equation, and this HCO3 exists in both equations, but I get it from the first because whatever I lost through the second will be negligible. If the second equation takes place, there's a minus y, if you will, here, and that amount is negligible relative to what I got from the first equation. Of course, I have the CO3, 2 minus, which is only coming from the second equation. And I have H3O plus coming from both, but we said that the amount coming from the second is negligible. And so let's get the H3O plus first, or H plus in solution. Since I got the pH, that's easy because that's then 10 to the minus pH. Okay, so you get the first H3O plus in the solution. And of course, you know that H3O plus should equal to HCO3 minus, because the amount again that we're going to lose from this is negligible. We also get H plus and HCO3 minus the same way we did with weak acids. Remember this equation I told you this can be useful for percent integration. That is the square root Ka times C0, remember? Well, if you don't, it's fine, you don't need it here, but I'm just showing it to you, you know, because this is another way to calculate H plus and the HCO3 minus concentration, which are equal to each other. These are X and X. And you get the same answer, right? The H3O plus from the pH is this, and the H3O plus from this equation is that. Don't forget, this equation is actually how the pH equals half pKa1 minus half log C got actually derived. What about my concentration of H2CO3 again at equilibrium? When we're talking here concentration of all species, we're talking about the species at equilibrium. H2CO3 concentration is simply initial concentration minus the X, minus X, initial minus X. Again, it would be nice for me just to put here C0 minus X, X, and X, just to remind you. And so I can just get that from C0 minus X, which is, guess what? This X is actually negligible. Didn't really make a difference when I did put it in, which we should have known, right? Because it is negligible. Of course, when you have H plus, you could automatically also get the OH minus. Oh, wait a minute. I don't see OH minus up here. Well, you don't, but you always have water in solution, guys. So if you have water in solution, water will also dissociate always and auto-ionize. And the amount of OH minus, in this case, is dependent on the amount of H3O plus inside my solution. So that would be Kw divided by H3O plus and get the concentration of OH minus in solution. One more species left, and that is this guy, CO3 2 minus. The only way to get him is through the Ka2 value, because he only comes from the second equation. The Ka2 is H3O plus times CO3 2 minus divided by HCO3 minus concentration, which is actually equal to CO3 2 minus only. Why? Because the H plus and the HCO3 are actually the same concentration. They are? Yes, they are, because again, the second loss or gain of H3O plus coming from the second equation is negligible. So the H3O plus is mainly from the first equation, and the HCO3 minus is mainly from the first equation as well. So this concentration cancels out with that one. And I can almost tell you all the time, Ka2 is always equal to this second species, A2 minus. Okay, so the Ka2 is always equal to the CO3 2 minus concentration. A little bit harder. I find you guys have a little bit more difficulty with bases than acids, all right? And here is an example of a calculation of the pH and the concentration of all species present in a solution of sodium sulfide. Okay. This is also part of your homework. This is number 21, part 6. So but I needed to give it as an example here, because really talking without an example is pointless, in my opinion, with calculation of pHs. Okay, so what is this? This is Na2S. What is that? That's a salt, right? Of course it is. There's a plus and a minus joined together. So first the salt dissociates, right, in solution. You end up getting Na plus, two of them, and S2 minus inside the solution. So what kind of solution is this? It's like the Na plus is a spectator, and what's the S2 minus? Yes, it's a base. It can't be acidic, so it's a base. What kind of base? Absolutely, it's a diprotic base. Why? Because it has two negative charges, so it can pick up two protons, possibly, okay, from water. And let's look at the two equations first. So the first S2 minus can pick up a proton, becoming HS minus, releasing OH minus. Then the HS minus also picks up a proton and releases another OH minus and becomes H2S. And no, it can't act as a base further. It's done. No more electrons. Okay. Lone pairs, but anywho, let's keep it at this for now. Okay, so did they give you KB? I need a KB, right? Well, I don't have a KB, but I need a KB. Now, why do I need a KB? Because remember, as with, see, with bases, we do the same thing as with acids, okay? So first, I want to see if KB1 is greater than 100 KB2. Why do I need to do that? Because then it simplifies my calculation of pH, because I could neglect the second equation and say the pH is mainly determined from my first equation, or actually POH, and then get pH. Where do I get the KB1? Well, pKa1 and pKa2, and actually this is the pKb1 will be 14 minus pKa2. Why? Because this species H2S and S2 minus is from the Ka2 expression for the H2S. Okay. All right. pKb2 is the 14 minus pKa1, because H2S, HS are the two donor conjugate for the Ka expression, Ka1 expression. These are the pairs for the Ka1. Okay, so once that's determined, is Kb1 greater than 100 Kb2? Well, what's Kb1? 1.1. So 10 to the minus 1.1. What's Kb2? 10 to the minus 7. Well, of course, this is way bigger than Kb2. And so what can I do? I can neglect the second basicity and consider the first equation as my normal weak base calculation, and I don't consider it at all as if it's a diacid. And so here's my equation, and that's what will determine my OH minus concentration, which will determine my POH and thus pH. Okay, so I put here C0 minus X, X and X, and which is the concentration at equilibrium for this base. And now I just treat it as a normal base. What's my second step? Yes, you guessed it. C is greater, or is it greater than 100 Kb? Is it? Well, check it out. Concentration divided by Kb1. Yes, Kb1. All right, this is 10 to the minus 1 divided by 10 to the minus 1.1, and I look at it. Is this greater than 100? No, it's not valid. Oh boy, not valid. So what is the equation that I have to use? Yes, what's the equation? Quadratic, absolutely, the quadratic. Because actually this is less than 100. And again, guys, just think greater than 100, less than 100. You'll never go wrong that way. Get a quadratic equation. And again, where did this quadratic come from? Yes, it came from the KB1, which is x squared divided by C0 minus x for this equation. You want to write down the species, that's fine, but that's it. And it if you forget it or you've simply memorized already this equation. Substitute in KB1, substitute in KB1 times the C. I find it easier to multiply it outside the calculator first. Solve for x by your calculator. That's all the calculator's doing. What is x? Yes, x is OH minus. So I need POH minus, which is minus log of my x. There's my POH, and then get my pH. Yes, a little bit longer because we're not used to bases as much, but watch out, okay? As important as acids. I want now all species in my solution. Well, you know what? I already have the OH minus from here. That's just OH minus is just my X. And my HS minus is also X, so that's also what's my H3O plus? Well, I can either get it from the fact that I have OH and then get it from the KW, or from the fact that I have a pH and then get it from there. Well, what if you made a mistake here? Maybe you'd better off get it from the OH minus, but then, you know, it doesn't really matter as long as you get it from either pH or from the POH, from the OH concentration. Again, where did the H3O plus come from? I don't have any H3O plus in my solution. No, of course you do, because you always have water, and water auto-ionizes, so you always get H3O plus. And now the concentration of H3O plus is determined by the OH that's already present in your solution. S2 minus is simply 0.1 minus X. Why? Because that's initial minus X, that's my S2 minus. Again, substitute, you got your X and you get a number. What's my last species that I need? Well, if you go back to the two equations, I still have one more species which is not determined. And that is this H2S species, which comes from the second base reaction. So that's going to come from KB2. So KB2 is OH times H2S times HS minus. And so solve now for HS minus. That's going to be KB2 times HS times OH. Well, this HS and OH are the same, are they not? Yes, they are, because we said some HS will go in the next equation, but that amount is negligible. Some OH will also be produced from the next equation, but that amount is negligible in solution. And so at equilibrium, these two guys are actually equal. And so they cancel each other out. And notice the H2S species is always equal to KB2 for a base. That's the same as the A2 minus species for the acids. That was equal to Ka2. Go back and check it out. Okay, guys, so you know what? I'm not going to remind you enough of this, but you already know this, right? This is weak acids, weak base, and that's the table I already told you about. I'm going to apply the same thing for diacids and triacids, but only in the case where Ka1 is greater than 100 Ka2. And for weak bases, that's the case where Kb1 is greater than 100 Kb2. And what is all this? That's what you already saw before. I didn't change it. It was just copy paste from the base. What's the difference? All you have to do instead of Ka here, just put Ka1. and here Ka1, and here you would put Kb1. What Ka value would you use here? pKa2, watch out, okay? So that's a little bit different, a little bit tricky, okay? Because Kb1 requires a pKa2. Okay, I'll leave you with that, and I'll actually fix this before giving it to you. Okay, well, take care, and your homework, I'm not going to leave you that early. This is your weekend homework. Number 9, number 20, number 27, and all of number 21 with all the species calculation. Okay, bid you farewell and take care.